Hello everyone, and welcome to section 5.2. We are talking about integration by substitution. So in section 5.1, we introduced the concept of the indefinite integral, the idea of taking an antiderivative of a function to obtain a new function or a family of functions. But sometimes we want to integrate functions that are too complicated to work with directly. So we try to find workarounds for situations like this. If we cannot solve a problem in terms of x, we can make a substitution for x with u. Then we can solve the simpler problem in terms of u and switch back to x. This allows us to take an easier antiderivative and still maintain a solution that ends up being in terms of x, the original variable. In general, when choosing a function for u, we want to look in the integrand for a function and its derivative. So the idea here, we're looking for a function and its derivative so that as we do our substitution, we can account for all possible values. So let's take a look at how this works in an example here. So this rational function, as is, to take an antiderivative of this would be extremely complicated, if not impossible, because you've got a quotient. You've got a function of x over a function of x. And the quotient rule does not undo easily. So what we can do instead is notice, if you look at the bottom function, 6x squared plus 4x plus 1, compare that to the top one. The numerator appears to be the derivative of the denominator. So what we're going to do is we're going to let u be equal to 6x squared plus 4x plus 1. Then when we take the derivative of u, we're going to use the Leibniz notation. Okay, so this like fractional notation, not like u prime or something. If we take the derivative of this, we bring down the 2, that's 12x plus 4 times 1. This is the numerator. So if we take the concept of like a differential, the idea of kind of moving this dx across to the other side, we end up getting du equals 12x plus 4 dx. So our goal here is to substitute all of these x's, all of these functions of x, for functions of u instead. So if we look at what we have here, 6x squared plus 4x plus 1, that's going to get replaced by u. So that's right there. That's going to get replaced by u. The remaining terms, the 12x plus 4 and the dx, those are both right here, 12x plus 4 and dx. They're getting replaced by a du. So we're going to get basically 1 over u du. So everything is getting replaced. And now you have an integral only in terms of u, not in terms of x. This is an integral that we can solve. So the antiderivative of 1 over u, if you remember from section 5.1, that's going to be the natural log of the absolute value of u plus c, so plus that arbitrary constant. Now, this isn't the final answer because the problem was given to us in terms of x. We needed to go through u in order to simplify our work, but we don't want the final answer to be in terms of u. But what we can do is take that original substitution, so u equals 6x squared plus 4x plus 1, and substitute that back in here. So this is going to be ln of the absolute value of 6x squared plus 4x plus 1 plus c. And that would be our integral. That would be the value of this integral. So again, an integral that would have been extremely challenging or impossible without a technique like this, where we can turn the complicated integrand, that function inside the integral, into a simpler function in terms of u, do the integration, and then switch back. For this next one, if we look at the pieces we have here, we have a 3x squared plus 5, we have an x. This can't be evaluated directly as is, so we need to come up with a substitution. Now, we really only have two choices here. You can let u be x, but if you're just going to let u be x, then you're just going to get the exact same problem with u's instead of x's, and that's not helpful. So instead, we'll let u be the 3x squared plus 5. So our du, so take the derivative, bring down the 2, that's 6x dx. So in terms of our coverage here, 3x squared plus 5 is going to get replaced with u. And we have our x dx is right here. But this isn't a perfect match, right? There is this factor of 6 here that does not exist in this integral. So what we can do, because this is just a constant, we can go ahead and just divide it over to the other side. So we get 1/6 du equals x dx. And now that gives us a direct replacement. So x dx will be replaced by the 1/6 du. So we get 1 over u, and then the x dx gets replaced by 1 over 6 du. We can pull the 1/6 all the way out to the front. So this is 1/6 integral of 1 over u du. And now this just becomes the exact same problem that we were working with up above. So 1/6 times ln of absolute value of u plus c. And sub back in the function that we know u is. So 1/6 ln of absolute value of 3x squared plus 5 plus c. And with this one in particular, because the x is squared and you're adding, we know that number is going to be positive, so we don't even need the absolute value on this anymore. It's not necessarily wrong to keep it there, but it is not necessary because we know the value will be positive. Whereas in the other one, there was not a guarantee of that. It could have been positive or negative, so we needed to keep that on there. For this next one, and actually these next couple here, we're going to work with exponential functions. So u-substitutions are a great way to also help deal with the chain rule and the undoing of the process of the chain rule. Because here we have e to the 3x plus 7, but the antiderivative of e to the x is e to the x. The problem is e to the 3x plus 7, if you take the derivative of that, it's e to the 3x plus 7 times 3. So it's not exactly the same. What we can do then is set up our u-substitution. U can be this 3x plus 7 up here. And du, the derivative of that, that's just the 3. So we get the 3 dx. So the 3x plus 7 gets replaced by the u. And the 3 dx gets replaced by the du. So this one works out quite simply here. So we get, this is just e to the u du, which the antiderivative of e to the u is just e to the u, plus that constant, of course. We don't know if there's a constant there, so we have to put the plus c. And then sub back in. So we know u is 3x plus 7. So we get e to the 3x plus 7 plus c. And as with any integral, if you're not sure whether you did it correctly or not, you can always take the derivative of this and make sure that you get back to the original version of the function. And that is what would happen if we were to test this. For this next one, notice we have a function of x times a function of x within the e. So let's set up the u substitution. Again, if we take the derivative, if we take u to be 4x, then the derivative is just going to be 4, and that's not going to help us get rid of the x's up in the powers. So we're not going to do that. We'll take u to be the 5x squared minus 2, so that whole term up in the power. Du, the derivative of this, is 10x dx. So what do we have here? The 5x squared minus 2 gets replaced with the u, and the x dx is going to get replaced, but it's not a perfect match yet because this 10 is still here. So let's go ahead and divide that away. So we get 1/10 du equals x dx. So this will be our match. Now notice with this one, something extra here. There's a 4 out in front. The nice thing is because 4 is just a constant, it doesn't impact anything. It doesn't change anything. In fact, you can just pull it out entirely. You can just pull the 4 out to the front here and now do the substitution. So we get e to the u times 1/10 du. So we're going to get 4/10. The integral of e to the u is e to the u plus c. 4/10, that's the same thing as 2/5. Sub back in, we get e to the 5x squared minus 2 plus c. And that gives us our integral value using the u substitution. So you can be off by a factor of a constant. That's not a problem. So again, like this extra 4 here, it didn't impact anything about how we took the substitution, how we did the antiderivative, any of that stuff. If there were more x's here, like if this was, x to the 5th or something like that, that becomes a whole different problem at that point. But constant factors, those can tag along without any repercussions. Let's look at one like this. So this is going to be a massive polynomial. In order to do this directly, we would have to multiply this one out 8 times by itself, and then multiply whatever that is by this, and then multiply the whole thing by 10. It would be a huge polynomial. So instead of doing that, we want to basically kind of take a chain rule type of approach here, where we can take an antiderivative without having to get rid or expand that 8th power. So for u, again, this one really is kind of the problem because it's trapped inside that 8th power. So let's make that the u value, 9x squared plus 2x plus 7. And then du is going to be 18x plus 2 dx. Which is almost a match. Let's go ahead. Notice there's a factor of 2 in here. So that's 2 times 9x plus 1 dx. And if we match this up, so everything in these parentheses here is going to become u. So that's nice. The 9x plus 1 and some of the 10, so a factor of 2, are going to be replaced by the du. Now, when we pull out the 2, we're left with a 5. So we're going to have 5 left over. This is going to be u to the 8th, and then du. And now this antiderivative, this is just a power function. So we take the antiderivative. This is going to be 5 over 9 times u to the 9th plus c. All right, you add 1 to the power, divide by that same number. And now just replace the u with the substituted function here. So this is 5/9 times 9x squared plus 2x plus 7 to the 9th plus c. So this is the value of that integral without having to expand everything out. So if you were to expand this answer out, like this 9th powered polynomial, and take its derivative, you would get back to here with all of these terms. But we didn't have to do any of that because we had the u substitution at our disposal. This next one looks a little more interesting. It's not quite as clear-cut necessarily. So we've got a cube root down here of 8x to the 4th minus 5. We've got an x cubed up here. If we're choosing... So the first thing to look at is, can we evaluate it directly? And no, it's too complicated to use our standard antiderivative formulas for it. What we're going to do instead, we need to choose what's going to be u. And it's pretty much got to be either this one or this one. So let's take, usually the denominator is a pretty good place to start. Plus, this is a 4th power, so its derivative is going to be a 3rd power. So that's a good thing to take note of as well. So we'll let u be 8x to the 4th minus 5. Then du will be 32x cubed dx. There is no 32 up here, so let's just divide that under both sides. So we get 1 over 32 du equals x cubed dx. So everything inside this cube root gets replaced by u, and the x cubed dx gets replaced by 1 over 32 du. So this is 1 over the cube root of u times 1 over 32 du. So let's see. The 1 over 32 is a constant, so that can just get pulled out to the front. The 1 over the cube root of u, so the cube root of u by itself is u to the 1/3 power. But because it's in the denominator, we're going to have it being negative, so u to the negative 1/3 du. So we have 1 over 32. Antiderivative of this, so we need to add 1 to the power and then divide by that same number. So that's u to the negative 1/3 plus 1 over that same number, negative 1/3 plus 1. And then the plus c will be there. It's just going to tag along here. So we have 1 over 32 times, this is u to the 2/3 over 2/3 plus c. Dividing by 2/3 is the same thing as multiplying by 3/2, so it's just multiplication by the reciprocal, like this. Of course, not a lot of simplification to be had from that. We just get 3/64 u to the 2/3 plus c. Sub back in what we know u is. So we get 3/64 times 8x to the 4th minus 5 to the 2/3 plus c. And then the problem originally gave us the radical notation, so we can go ahead and put the final answer in radical notation as well. So it's 3/64 times the cube root of 8x to the 4th minus 5 squared plus c. And that would be our integral, so our antiderivative for this function. So still using a combination of like the power rule and the chain rule and undoing the effects that they have on a function in taking the antiderivative. And then lastly here, we've got one more, kind of an interesting case here. So you've got x times the square root of x plus 3. Now, when we're making our selection for u, again, choosing x by itself is not helpful, because if you let u be x, then it's exactly the same problem, but with u's in it instead. So we're not going to choose u to be x, but we do have this x plus 3 term inside the radical that is a little bit of a problem. So let's go ahead and let u be x plus 3. When we do that, so the derivative of x is 1. So it's just 1 times dx. So du is just dx. So we get u is the x plus 3. Dx is getting replaced by du. And now we have an issue. We have this factor of x here in the front that is still there. And if we were going to set it up this way, this wouldn't work. You can't have u's and x's together in the same integral. So we need to figure out how to turn this into u's somehow. And this is where the substitution is going to help us again. So if u equals x plus 3, and we need to find what x is, solve for x. So subtract the 3, we get x equals u minus 3. So our x can get replaced by this. Get replaced by a u minus 3. Now you might think, well, that doesn't sound much simpler than the original one we started with. However, this u minus 3 out here is not under a radical. And that's going to make this solvable, whereas this one was not. Because now from here, the radical u is going to be u to the 1/2. So we can distribute that to both of those terms. So we're going to get u to the 1 times u to the 1/2. That's u to the 1 plus 1/2, which is 3/2. So we get u to the 3/2 minus 3u to the 1/2 du. And now we need to take the antiderivatives. So we get u to the 3/2 plus 1 over 3/2 plus 1 minus 3 times u to the 1/2 plus 1 over 1/2 plus 1 plus c. So plus that constant, of course. 3 halves plus 1 is 5 halves. So we have u to the 5 halves over 5 halves minus 3 times u to the 3 halves over 3 halves plus c. Use multiplication by the reciprocal for these. So this is 2/5 u to the 5 halves minus 3 times 2/3 u to the 3 halves plus c. And it's mostly just algebra at this point, so cancel the 3's, which just do that right now. So this one, we're just left with a 2 there. And now sub back in. So we know that u equals x plus 3. So put x plus 3's back in for u. So that's 2/5 x plus 3 to the 5 halves minus 2 times x plus 3 to the 3 halves plus c. And again, this is a perfectly acceptable answer, but just for the sake of consistency, the problem gave us the form of a radical, so I'll go ahead and keep that form. So we're going to have the square root of x plus 3 to the 5th, and then minus 2 times the square root of x plus 3 to the 3rd plus c. But again, there would have been nothing wrong with leaving it as a fractional power as well, as long as it's not a negative power. Negative powers we don't want to leave in that form. We want to make them positive, but a fraction, that's okay. It's just representing a radical. Okay, but that brings us to the end of section 5.2, and that's kind of the conclusion of our introduction to indefinite integrals. And in section 5.3, we'll be looking at different types of integrals and how we can start applying them to different contexts. But that is our section on substitution.